So shall I start? Okay, so we were considering the following problem. You can think of it as the Stokes problem, non-stationary Stokes problem. And so what is the equation that we have? Derivative of u with t is au plus sigma dw, right? I can put some dw of t here so that dw of t. All right. Is that all there was? Yeah. That's what we are considering, right? And u of 0 equals, what did I call it? Some x, h, where h is a separable Hilbert space, and A is the generator of a strongly continuous semigroup, and sigma is a continuous operator from h to h, and W is a Wiener process. So W is we call W as a cylindrical Wiener process. Therefore, it acts on all orthonormal directions according to a one-dimensional Brownian motion. EJ is complete orthonormal. Any complete orthonormal system. Complete orthonormal system in H. So then we call it as a cylindrical Wiener process, and sigma, as I told you, is just a continuous operator from H to H. And what other conditions did we put? Do you all remember? We needed some more conditions, such as A times x is from h, so I'm going to write it as h, is contained in q to the half h, right? What did we call it? Yeah, q to the half h. Correct? So we needed this so that we can do the Gersonov transformation, which was essential to prove Strong-Feller condition and irreducibility, one or the other. So for irreducibility, we got it for free because it was so simple. But then for Strong-Feller condition, which is a condition about smoothing property of the semigroup generated by A, then we needed such a condition. Okay, so what was our solution itself? It was in the mild sense because sigma is just a continuous linear operator, so we cannot give a meaning to this. We need some help from A, right? So it is e to the ta times x plus integral 0 to t e to the t minus s a sigma dw of s. Correct? So we call this as the stochastic convolution, and the notation was z sub t, right? You all remember all these, huh? Now we shall, we have proved actually the Strong-Feller u of t. Okay, first of all I have to say st is the semigroup generated, st is, I'll come to that. We proved Strong-Feller property. What does that mean? S sub t maps bounded Borel measurable functions on H to CB of H, right? Where what is S sub t? S sub t of phi is nothing but expected value. Let me also put a little x there. It's not the same x necessarily, or I can even put an h. But h looks like a function, right? Maybe y. It means you start at y and you have to find out. So I don't need to put it necessarily here. U of t y. So this is the process. It's a stochastic process adapted to the filtration f sub t, whatever is given. I haven't even shown you the omega ft, fp, script ft and all that because, pardon? Oh, I just took any y member of H. It's the starting point. Namely, instead of little x, if you take y, the solution is called u of ty. So just wanted to emphasize that you can do it for any little y member of H, and this is the, if you are solving this with initial condition to be y, let's denote it by u of ty at time t, and this expectation is precisely S sub t phi. And it's a semi-group because of Markov property. Why Markov? Because there is not much to disturb anything, right? There is only this additive noise. So simplest case. Huh? Oh, I just put a y. I don't know why. I could have put for all x. You are right. So in short, we are talking about a family of stochastic processes, which is called the Markov family, right? So this is the property of which we call a Strong-Feller, okay? And this should hold for all t greater than 0, right? So there is a smoothing property. That's not a big deal. We would expect at least that much from the semi-group. If you look at the Heer equation, you get the Gauss kernel, right? And then it smooths out things. And irreducibility, what did it mean? It means you should be able to go from anywhere to anywhere else, right? In the vicinity. Very good. I didn't let you say it. Huh? You knew it. And I have a way of being dictatorial. Okay. So it is the probability of, okay. You start at little x, right? And you take any t, maybe t. And then you should be able to go to any R ball around any other point z with positive probability. That's the idea, correct? And it can also be couched in different ways. Okay, so why did we prove Strong-Feller and irreducibility? Because there was Dub's theorem which said if there is an invariant measure, and if we have Strong-Feller property and irreducibility, then the measure is ergodic, right? Yeah. Correct. For all z, r, and t, open. Xz positive and also t greater than 0. Yeah, I can weaken things. Yes, I am putting a whole lot here so that it's all neatly stated. You're right. I can even have irreducibility at a particular point and so on in time. All right, those are finer things. So as I told you in the first lecture, I'll just put whatever I want to, and then the refinements are up to us. This is an area actually wherein there are so many papers written up, okay? Invariant measures for stochastic PDEs, especially Navier-Stokes. There are a lot of papers. I think each one of us wrote at least one. And kind of saturated, but then there are important things that are still open, such as properties of the ergodic measure. And also in the three-dimensional case, the 3 dimensions yeah, it is done. Yeah, Debouchet and Deprato have a longish paper using Kolmogorov equations, and they, under certain conditions on the noise, which is additive, obtain the, you have to take a certain selection of the process, and then there is an invariant measure and so on. Okay. I won't discuss that. That's too technical, and if I want to, I can summarize the results later on. Okay, so we still need the existence of an invariant measure, right? If you look at the Dub's theorem, there are 3 things. It's not just Strong-Feller and irreducibility gives us an ergodic measure. You also need an invariant measure, right? So we define the following operator. Okay. I stated only one condition, right? there is also one more condition to say that this zt is well defined and takes values in H, right? So that condition was we computed the expected value of zt squared, and what did we get it to be? Trace of qt, trace of q sub t, and we wanted it to be finite. What is qt? It is the integral 0 to t e to the ta sigma sigma star e to the t a star. You put everywhere t, right? ds. It's really t minus s. T minus s. Okay, because there is a t minus s here, right? So I'm just wanting to be exactly as it was done before. Though I could have put an s there, it doesn't matter, by a change of variables. Okay. So, now, so this is also an assumption, but it's not a big assumption. Without it, you have to make sense of the given equation in somewhere or the other, right? If it is not defined anywhere, it's a problem. So, now let's make another assumption. So I told you all that you can look upon this as the Stokes problem, right? Stokes problem will be an elliptic problem, right? And this is the parabolic version of it. That's why I call it as the linearized non-stationary Navier-Stokes equation. That's how Ladiszynskaya would call it, right? And assumption is that e to the ta, right? It is less than or equal to some k times e to the beta t, let's call it, where beta is less than 0. That k is greater than 0, I don't have to tell, it's obvious. Is that a big condition? If you take A to be the Stokes operator, think about it, right? So we are only talking about the mild solution. Why are we only talking about the mild solution? Because I was just making it such that sigma dw, the integral of sigma dw was undefined, right? So by putting this condition, only the convolution integral, the stochastic convolution would make sense, correct? That's all there is to it. Okay. Now, in order to identify the invariant measure, we will go to the following, we will define the following process. Define. Before I define, let me say first. Okay, the word define was actually correct. Define q infinity to be integral from 0 to infinity of all those things. Okay, e to the, I don't have to call it as t minus s. If you call t minus s as some u, again you'll get the same thing, correct? So, e to the ta, sigma, sigma star, e to the t, a star. All right. Then, let's see if the trace of q infinity, what it comes out to be. We have now an extra assumption here where beta is negative, right? Do you all see that this is just the extension of these? If I put a q sub infinity, this is what I would get, right? Because the t minus, just a change of variables, nothing else. So trace of qt would be, how to define? So first of all, qt can be written as a summation, j varying from 0 to infinity of integral from j to j plus 1. Right? And j to I'll make it as 0 to 1 and call it as j plus s. J. Right? I'm just, in each one I'm changing the variable. Nothing much going on there. Okay, what should I do now? I'll just keep the JA here. And then I have the, no, e to the JA doesn't need an integral, right? It is only with respect to S. Star, yeah, where did it go? Random errors. Okay. And this is exactly called as Q1, correct? And therefore take the trace. Now the e to the JA, e to the JA star, I can use this bound, right? And then trace of Q1. Trace of Q1 is finite, and then this beta is negative, therefore it's summable, and everything is okay. Therefore, the Q infinity is a trace class operator. Now let's define a process f sub g. So when I'm defining something, you can all take a breather, right? Nothing to think about. Same way here also, but then this is just a small calculation. Did you all understand this? All right. Yeah, you are all experts on functional analysis, so you should be able to leaf through and then readily understand, right? Or right away, probably you're all thinking it's too simple. Okay. The convolution integral that we had at a t minus s, right? If I just put an SA, sigma dws, whether it is subscript or over here, it doesn't matter. It's all the same. Then notice that mt and zt, namely the stochastic convolution integral that we had, and this stochastic integral have the same distribution. How would you say that it has the same distribution? Because they are normal, therefore they are parameterized by two quantities, right? Namely the mean and the variance operator, and they coincide. We are done. So mt has the same distribution, probability distribution, as zt. Now, very simple result. Therefore, I will just show you the proof. Limit of mt as t goes to infinity is the exists. I will try to write this. Exists, and we can call it as m infinity. Proof, how would you prove? Oh, in what sense? That's the question. You got to ask me questions, right? Otherwise, I'll keep on doing. Yeah.
Before you raise that last line, that k is actually 1, and beta is the first eigenvalue of the Stokes operator.
Exactly. Right. That's right. That's right. Yeah. So for the very good. Connecting it to the Stokes problem. This e to the beta t can be replaced, beta can be taken to be lambda 1 t, where lambda 1 is the first eigenvalue of the operator, Stokes operator A. That's all there is to it. K is just 1, right. K is just 1. Yeah. Good point. So you just think of the particular case when the Hilbert space H was defined by Professor Sridharan, right, in the context of Navier-Stokes or Stokes. has the closure of very smooth functions with compact support such that divergence is 0, right? And then close it in the L2 norm, you will get H. So, so proof is, I was going to tell you why, in what sense, it's in the L2 sense. L2, how to call this L2? Because they're all H valued, take the L2 norm, and so these are all random variables, right? Okay. So simply consider this. MT minus MS square. Now you are all experts on this. This should be some trace from integral from S to S plus T and so on, right? Shall I leave this off? It's an easy proof. Yeah. If you want me to, I'll do it.
Navier-Stokes spaces V and H.
Oh, I didn't say anything very valuable. I just like to talk. The H is just the L2 space where divergence is 0 in the distributional sense. Yeah, and it can only see the boundary condition through the normal, right? The exterior normal n, right? V dot n would be U dot n would be 0, right? Yeah. That's a characterization. But then if the characterization is too difficult, take it as the definition. Then you don't have to know how to prove it. Okay. So compute this and then show that this goes to 0 as S goes to T. Right? You can take S to be less than or equal to T. Why? Because the letter S comes before T. Okay? And so work with the trace, it should be fun. All right. And next result. Oh, I haven't been using this board. It made a point of it, but I was missing this. So the second one. S sub T phi of x. Okay. Converges to the distribution of M infinity. Okay. So the law of M infinity can be shown to be normal with 0. It's not quite right. Okay, let's see where it converges to, and then I'll write the result. I was going to write something. Proof. You don't know what I'm proving, so I can do whatever. Okay, S sub T phi of x. It is nothing but the expected value of phi of u of tx. Correct? And this is expected value of phi of, what is u of tx? It is e to the tx plus, what else? Zt. Tell me if you don't agree with anything, something that I write. Not anything, something that I write should be okay. Now, when you're taking the expectation, this is a deterministic quantity. Zt has the same distribution as Mt. Zt is a stochastic convolution, Mt is here. What is the big difference? I didn't put a T minus S, just put an S.
Yeah, sorry.
Yeah.
You proved that Mt is a distribution.
Yeah, because they are normal, mean 0, and their variances coincide. So we know it explicitly. Yeah. And therefore, since we are taking expectation, I can also do this. Because they are the same random variable. As far as expectation is concerned, you just need the distribution, right? Therefore, S sub T phi of x, okay, converges to, if you take t to be infinity, here we've showed that it actually converges in L2. Therefore, it definitely converges in distribution. And if p is a bounded continuous function, then I can just do what? How do you pass limit inside the expectation, where expectation is an integral? What theorem do you know? Dominated convergence. Right? And for dominated convergence, you should know that the underlying variables can just converge in distribution. It's not necessary that they should converge almost sure. So, and this part, what happens to this? As t goes to infinity, it is going like e to the beta t, remember? Therefore, it goes to 0, and this goes to m infinity. Right? Sense. Everything by Lebesgue dominated convergence theorem, and this is nothing but integral of phi of y mu d1 say. So I can implicitly said that distribution of m infinity is mu, right? So what do I need to write here? No. Where mu is there, where first of all phi is in CB of H, and mu is what? Mu is the law, the distribution. Sometimes I'll call it as law. Okay. Since we do it so often, we have so many terminologies in math, in probability theory. That's how we confound others. And so now this actually almost points out that mu is the invariant measure, right? So the next thing is to show that you can now prove that another proposition could be, or theorem could be, that mu is invariant. What is mu actually? What kind of a law is that? It's what is the distribution of m infinity? Okay. Normal or Gaussian, however you call it. 0. Right. So that's what we call as Q infinity, right? Is the invariant measure. Is an invariant measure for ST. Right. So, how to prove this? You can now, we almost have it, right? The repeat of the same kind of proof by dominated convergence and so on will show that what do you need to show? You start with mu and then look at what has happened on an average at time t. That should be the same. Okay. Proof like the previous result. Shall I just say stand as before? As before meaning similarly, you can just work it out. It's not a big deal. Okay. Now the final theorem. So that we can get out of the Stokes equations here. Mu is a unique ergodic measure for whether I call it ST or XTX, it's up to, right? I like always to be in touch with the random variables. right? For me, the semigroup S sub t is it arose from the x sub t super X, so it's a close cousin of the variable. It's not the random variable. Right? So how to prove this?
Solution, right?
Pardon?
T is actually U of x t according to your previous.
Oh, yeah. U of x. Yeah, that's what I meant. U of tx or xt, whatever you are, right.
U was H.
Huh?
X in H.
X in H. Yeah. We left off this other space E. H. So the proof is how can we prove? Well, it is an invariant measure, mu. We have already proved irreducibility and Strong-Feller. Therefore, it's an ergodic measure. Then one can also show that there is only one invariant measure, because if xi is a random variable, okay, with law of xi to be any measure nu, probability measure nu, then we can show that the law of the distribution of u of tx super xi, L T z, that is, I'm starting with this distribution, okay, would converge weakly, you know the weak convergence of measures, to mu. That we can show. I'll leave that as an exercise. Now we have a lot of exercises, right? So exercises are usually for you, though we can prove it sometime. Okay. Exercise. Therefore, using this, one can show that it is, therefore there exists only one invariant measure. This is there in my notes, okay? So all of these, I don't have to prove anything. I don't have to even think, because I have to just look at the notes that I posted for this. So it's there. So if there is only one invariant measure, there can only be one ergodic measure, because ergodicity doesn't precede invariance, right? You need an invariant measure to show that it is ergodic. Also note that if you have normal 0 q infinity, and we have all along been taking Q to be full, namely its kernel is just 0. Therefore, its support is everywhere, right? So if you had to come up with another ergodic measure, it has to be singular with respect to it, right? So it has to be like a point measure or something. That's not going to happen. All right. Anyway, this completes the proof. So everything is due to the Toops theorem here. So Professor Vaninathan wanted to know something about invariant measures. Of course, in the simple case, it's tractable. Namely, it's Gaussian. If things are just Gaussian, that means we are working with a simple case. It has to become non-Gaussian, and that happens with some non-linearities which are introduced, right? Okay. Any questions so far? Oh, definitely. Yeah. Correct. That's right. So it could be, or there has to be non-linearity in the dynamics and the drift part. Right? It can then create some disturbances.
How do you relate this with the example of Where you take XST, whatever it is, solution to the okay?
Yeah.
And you choose an X as some minus alpha times dt plus something, right?
Very good. Yeah. That's right.
That's the DWP. Now you choose an alpha to get a
right. That's right.
But I don't see this alpha here.
Yeah, the Q infinity. The Q infinity contains information about all the alphas we have put, namely the lambda j's, which are the eigen values of the trace class operator Q, right? So in that way. So you got to look at it in different, coordinate by coordinate in the orthogonal system. Yeah. All right. Yeah. Correct. Yeah. That's right. Mm-hmm.
Here you take any arbitrary point and then you take the limit t tends to infinity. So it is independent of the x.
For any little x, yeah. So like here, z can be anything here, right. Then u, yeah, and still it converges to mu.
There you choose on initial point depending on alpha, and then you get a.
That's right, because there I was only showing the stationarity of the distribution. Whereas here we are claiming it's ergodic, which means you need not necessarily start at the optimal. So initial distribution won't be the same as the next time point. But then after a while, the time averages smooth it out. And then, yeah, so that's the ergodicity. Yeah.
Your initial example, the initial point was a random variable.
Right. No. If you start once again exactly here, if your nu is coinciding with, let's say, if it coincides with this, then you get a stationary process. Right. And stationary processes are very nice from the point of view of ergodic theory because there is the shift transformation and the measure is preserved. These are called measure preserving transformations, right? I skipped all those and went in a funny way. Yeah. One should really start with measure preserving transformations, right? Yeah. Okay. This one erases better, but I couldn't find it. They say, right, if you see a dog, you don't find a stone, and if you find a stone, you don't find a dog. It's not to hit the dog. You know the proverb, right? It means if you see it as maybe it's a dog made out of a stone, right? And if you think it's a stone, it's a stone. If it's a dog, it's not a stone. You just see the dog. So I'm not being cruel here by saying that. Okay, so now we'll come to something non-linear. Okay, but I know that this is not going to make Professor Vaninathan excited because it's just a Lifschitz nonsense. I mean, non-linearity. Okay, so T dt plus, let's say, sigma dw of t. Just as a trial case, right? Where f is non-linear, okay, A and sigma have the same conditions as before, and f goes from, I had to say what is u of 0. It is little x, member of H. So you can put you know what I mean. And sigma is going to go from, f. F of x minus f of y is less than or equal to k times. Okay, then this is just Lifschitz nonlinearity. So I can call it a semi-linear equation? How do they call it? That's what it is? Okay. Okay.
Sorry.
That's all right. Yeah. Have a pleasant flight. And so what do we do in this case? Solvability is not a problem, right? You just, okay, but what is the solution? That's all I wanted to write. U of Tx, once again, it's a mild solution. plus zt. Or you can just call it as zt, right? The integral of e to the t minus s, sigma dw. So this is, then I can just write it here and say space. So this is my solution. Solution exists, it's unique and all that. How do you prove it? Yeah, fixed point or Grunwald lemma is always there, and we are happy. Okay. You can also make approximations and show that it also converges. For instance, you can zt. So in the Brownian motion, you can truncate it at time. So you can take only n orthogonal directions, so that it's a finite dimensional noise. Okay. So you can define un. It corresponds to, I don't have to write the whole thing. This equation corresponds to wn, which is summation of ej, bj of t from 1 to n. Then uns will converge to u and stuff like that. Okay, I'll tell you in what sense in a second. And then you can also do the following, unm. And that would correspond to not only wn, that is, you all understand what this symbol means, right? You put this wn here, and that's the, and then solve it, and the solution is called u super n. U super nm would be, it corresponds to not only wn, also make this is am, where am is the Yoshida approximation. You all remember Yoshida approximation for the operator A? Professor Adimurthy showed it, right? And it's a bounded operator, right? So it's easier to work with, and it converges to A. And what is AM? Anybody remember? A lambda or A, whatever. You can write it in several ways. You can write it this way. So why do I write it this way? I thought Professor Adimurthy wrote it more nicely. I write it this way because I'm a probabilist. This exactly corresponds to the infinitesimal generator of a compound Poisson process with dynamics given by I plus A over M to the minus 1, and M is the waiting time parameter.
Sorry, now I am interested. Can you repeat?
Again, I didn't say anything valuable.
The infinitesimal generator of the compound Poisson process.
Right, where the jump mechanism gives you this kind of an operator, I plus A over M to the minus 1. You should always have, in a compound Poisson process, the generator would be like this, lambda integral. If you are operating, if the operator is, let's call it as B. B is operating on F. Okay, L is a good name for it. LF, lambda LF of X. Lambda is the waiting time parameter, as we call it, before jumps occur. Time between jumps, right? They occur according to a Poisson rate, and nu is the jump distribution. Okay. So, but they all boil down to the same thing. Okay, we have to go fast. So what was I telling you? Oh, I just then limit of u sub n as n goes to infinity is u. Things like this. You can prove easily. In what sense? In the space of continuous functions. Let's just take a 0 to capital T. So we want to look at this equation maybe on the interval 0 to capital T, where T is arbitrary anyway, all right? So so it will help me to write all these things here. So when I put like this, that means the soup norm is involved. Just to confirm, let me also put AD there. That means additive. Oh, sorry. What is it? Adapted. So I'm looking at all measurable, jointly measurable process is what I call as a process. And it is also, it has got to be adapted to the filtration. And it has to have, and then I'm looking at the norm in this space. Namely, when I put C, it is the soup norm. And then the L2 omega H, you all know. Right? Okay. So that's about, so solvability and all I'm not going to do. It's all easy. So since I'm skipping some things, okay. But everything is explained in the notes. Modulo typos, as I told you. Okay, there are typos here and there. Some harmless, some bit serious, but you can see it. It will look funny, and then you can correct it, and that can be an exercise. Okay, I will also do that exercise though. Okay, U of Tx. A very minor result. I won't prove this. Again, it is what is it called? Grunwald inequality. For some k. Maybe k depends on t. T is 0 to t. And so on. And x and y, you know, number of h. That's not a big deal. So u is continuous with respect to the space variable. Why? Because when you subtract, this goes away. That's the beauty of additive noise. There is nothing coming from it. If it is multiplicative, you get to worry about all kinds of things. Okay, and this is Lifschitz, and this goes away because you're writing in the weak and the mild formulation. Okay. Now the question is differentiability of the solution. So whatever I don't say here is covered in the notes. So I don't have to mess around with what's there already. For Z member of H. D sub Z of Tx to be the derivative of the process U, okay, with respect to x, and then you are going to hit it with Z. Do you all understand what I wrote here? I don't know whether it's differentiable. That doesn't bother me. I write it and then prove that it's differentiable. I won't prove it. It's there in the notes. So what is this du? It is actually differentiability with respect to initial data, right? And that's very scary because this is a stochastic process, and then how do you differentiate? But then there has to be some differentiability property in some sense, in the mean square sense or whatever, right? Okay. So you don't even have to go there. It was even proved in finite dimensions, for instance, in all the books of Skorokhod, Gichmann and Skorokhod, right? And then Daprato in infinite dimensions, Daprato and Zabchik, right? And so many places you can find it. Okay, so I'll write something more. I'm right now just announcing. But before that, what is du? Where does it take values in? I'm doing the derivative with respect to x, not with respect to t. That doesn't exist. So what is the where does my u take values? H. So it's h-valued function of little x. So it's a h-valued function of x which lies in h, right? And so you had to take the derivative, and where would it lie? So u is, okay, let me write down here. U of t. That's what you told me, right? So I take the du of t. Where does it take values? Very good, very good. That's what I wanted to hear, and it has to go from h to where? To linear operators on h, right? Correct? So then I take the du and then hit it against z, where z is in h. Therefore, this is h valued. Correct? Okay. You all understand?
But Z is a process, right?
Z is just a point in the Hilbert space. Because there is a Brownian motion. Brownian motion has only derivatives of order less than half, right? Is that right? The precise growth of it is given by what's known as the iterated logarithm, law of the iterated logarithm. So you can divide it at most by square root of t log t. But then those are finer results. You don't need it for doing SPDEs. Okay. So here is a theorem. Before I state the theorem, let's get our mind's eye. If you try to differentiate this with respect to x, then what is the best way? If you are all the time worried about technicalities, you won't get anything done. So do it like an engineer, right? And namely, just take the derivative inside and all that. So it becomes dv, right? And then you are, of course, taking the inner product with respect to z or whatever, right? I don't know. Then you got to have z also, right? So here, if you simply differentiate, it will become dv, right? dvz. Z is just coming in later, but then I'm just putting it. And here also you can take the derivative of x inside, okay? dz. Is that how I wrote? Yeah. How about here? I need some differentiability of capital F, right? And then what else? And then I'll do the, what is it called, chain rule. Derivative of u is called vz, right? When it is evaluated at z, I'm also doing the evaluation as well. Should I put something else? dt.
Are you doing shading?
Yeah. And what is the initial condition? So if you differentiate this with respect to x, what should you get? It's the derivative of u, right, that we are looking at. The derivative of u at time 0 would be derivative of x with respect to x, which is I. And therefore, I am hitting it against z, therefore it will become z.
You can just differentiate. You are sure you can just say, okay, the differential of AB is the AB, the differential of B?
Yeah, because... Right. I'm just looking at a candidate right now. I told you I'm doing like an engineer. I'm doing formally some calculations. And then I will write it as a theorem. Then I have to worry about sufficient conditions under which I can do this. Right? Yeah. So let F be, so the theorem is as follows. If F is in CB2, I need only one derivative here, right? but I take it to be kind of two derivatives so that I can make bounds and then use the dominated convergence theorem or whatever. And then u is differentiable at x. Differentiable at x and
the question about differentiability effect? I didn't hear.
Oh, yeah. CB2, meaning it has to have two Frechet derivatives, bounded derivatives, and then when I'm going to estimate some approximations, the df minus df can be bounded by the second derivative.
So as far as Navier-Stokes nonlinearity, for example,
right,
it is real analytic because in U, U is a U dot gradient U is real analytic. You can take as many derivatives.
Right.
So that question is a little bit more abstractly.
Correct. Yeah.
Here the physical problem, it is with respect to U, it is nice, well behaved. So
Right.
that's the equation
Right.
of the Frechet derivative.
In general, you need some condition on A to do it, right?
Yeah, I had so many conditions on A.
You cannot just put the differential.
You can, but
Yeah, but it's not a.
Not for any
the
contractions.
equation Sundar wrote for the derivative, Frechet derivative, is even a simpler equation than the Navier-Stokes. It's almost like the Stokes problem,
Right.
right? For Vx. So it's
It doesn't present difficulty. So in this simple case, you can take the derivative inside. Yeah.
Does it work for any contractions?
what was the question?
Oh, she wants to know if it works for all contraction semigroups, generators. Yeah. Generator a contraction semigroup. Yeah, it should.
Because if
I know that it is done
Right.
by someone, but I don't think you can just put the differential inside.
That's right. That's not how I do. Yeah. If you look at the proof of the theorem, it would say what to do. Yeah. I don't take it just like that. Yeah. I take first the differences and then take the limit and show that this is the equation that we get.
If you take just the differences, you do that too.
That's right.
Well,
Yeah. But you can get. Yeah. You can get it.
Frechet derivative satisfies the equation E rho, right? That's the linear equation dvx equal to avx plus dffu vx.
Yeah.
Formal.
Yeah.
Now, you go and prove solvability just like you prove solvability for either Stokes problem or
Right. Exactly.
Navier-Stokes, which validates the fact that there's a solution and the vx is, in order to show that v has a Frechet derivative, you have to show that it is a bounded linear operator and all that. So
Yeah.
those conditions are satisfied.
Yeah.
So by proving the solvability of the formal equation E rho, right?
Right. So it doesn't present. You can look at the proof and tell me. And du would exactly be du evaluated at z would coincide with vz of tx, and this would solve this equation. Solution of, well, let's call the original equation as 1 and this as 2. I don't take just derivatives in one direction and all that. And I am announcing that this only for fixed z. I'm having a z in mind, and then I'm taking the derivatives. Vz, which solves 2. And these are routinely done in Kolmogorov equations in infinite dimensions. All right, so it's not my result, or it's a general result. So what I'm saying here is all very standard. And how do we interpret the solution of this 2? Again, in the mild sense. Solves 2 in the mild sense. Okay, so and one more very important inequality that we also get is Vz is less than or equal to some constant times. This absolute Z is my norm in the H, in the Hilbert space. So it's the Hilbert norm. Okay. Now, for all Z member of H, everything. Okay. So we are only interested in the Strong-Feller property and irreducibility, right? Because that's what we want to apply the Dubs theorem.
Sorry.
Yeah.
One comment.
Yeah.
That this equation has a solution, it's okay, no question.
Yeah. And then you got to identify
The
this.
point is to show that the solution you had before is differentiable and is the solution of this.
Exactly.
This is the second question.
That's right. Everything is, I stated it very compactly here. All of them needs to be proved. Yeah. So it's not just a question of solving that simpler equation that we got, namely equation 2, but also show this equality has to be shown. Yeah. Correct. Okay. So let's get a little bit to Strong-Feller. Strong-Feller property. So what is the semigroup that we have? St phi of x. You all know this. Just write phi. Okay, otherwise it looks like empty set. Okay. And see, the proof of this theorem, you have to make these approximations that I told you about. It is not, I misspoke when I said I take differences. You take this UNM and all that, namely, make the noise to be finite dimensional, and also take instead of A sub n, which A sub m, where that's the Yoshida approximation. Then do it. And then you have to take the limit. It is in taking the limit that you encounter this condition. Things like this, right? So there is no problem with Fréchet derivatives. Because you work with bounded operators and then go to pass to the limit to unbounded operators. Happy?
Yeah.
All right. Okay. And Strong-Feller is, we got to show that, okay, in general it can be defined for all phi member of bounded Borel measurable functions in H, right? And X can be any H. Is St Feller? What is Feller? CB to CB. That's easy. Of course, I keep saying everything is easy or something. And I don't mean it's simple. It's simplistic, but you can sit down and do it. And St is Feller. Whether it's Strong-Feller is the harder part. Okay? And there is also the convergence of the corresponding semigroups and so on. So I'll just write for instance this S super n sub t, where this corresponds to making the noise finite dimensional. Put as n goes to infinity, St phi, point by point.
First, you deal with the Yoshida's approximation.
Right. Yeah, you do those both of those, and then pass to the limit. Since there is all these approximation schemes, right? They are good approximation schemes, and then show that everything converges to the correct limit. And same thing you can do for STNM also. If I put an N and an M and then make this as M, this would be All those are there. I'll just write the neatest one. Okay. Okay. I just want to say only a few things. Okay. So, underlying this proof of Strong-Feller, there is this formula of Bismuth-Elworthy, known to everyone who works in this area, maybe. And just TFEs. So, if we, before I go there, supposing you just differentiate ST. ST phi of x comma z. This is the inner product that I have put there. And it so happens that ST phi is differentiable if you take phi to be continuous. And what does this come out to be? You can write it as expectation and so on. And the expectation can be taken outside. You can prove all these. Expectation of phi of u of tx. Again, I have to do the differentiation. I can bring the differentiation actually inside. You can show all these kind of things, for instance. Since deceptive phi is differentiable. Phi is CPFH. Things like this. CB1 rather. CB1, because I had to be able to differentiate. All right. Let me, huh? Yeah. Yeah. Yes.
Because this formula.
Yeah. It would be in the sense of Radonic derivatives. Is that what you're thinking? Maybe meaning derivative of one measure with respect to another? Yeah. That's right. That's right. Correct. That's right. Malyavan derivative, you can only do it in some directions, right? Yeah. So here we are talking about, yeah, right. That's why I'm hesitating. Yeah. So what is this Bismuth-Elworthy theorem? We will do this, and I'll just give a sketch of the proof. So it's proof within inverted commas, and then go to Strong-Feller, and finally irreducibility for these. Okay. So let sigma inverse exist as a continuous and be a continuous operator. Right? Then dSTZ for phi member of CB2 dST phi of x. Okay, that's it. And I will put an expectation because here there is nothing random. This is an excellent result if you are looking at it for the first time. Where is phi on the right hand side? You can ask, right? There is actually. I forgot to write. One second. The main thing is missing. 1 over t expectation t. So there is a bracket there, and I had to have a bracket here. So what's the nice thing about it here? See, here there is a derivative, right? And the derivative should really involve the derivative of phi. But when I want to prove the Strong-Feller property, phi is going to be just bounded Borel measurable. So how on earth am I going to differentiate phi? So what this says is, though it is known to be, it should be given by this, okay, which the left-hand sides are the same. So it should be given by this, but actually you can couch it such that phi is not differentiated, right? So that's very good for passing to the limit from CB2 functions to bounded Borel measurable functions. Correct? Now, how does one, I don't want to show the full proof, no, it's not. Since you are seeing the derivatives of processes for the first time, right? Probably. The proof is as follows. So if you have, let's say, a function f, take a function f, but then do this semigroup. I can actually do it on phi. Let me. ST phi. What is it? It is the expected value of phi of u of x. Correct? That's what it is. That's our definition of S sub t. What is little x? Little x is what we call as the backward variable, because that's where we started from. Okay? So starting position, therefore backward. And t is not the backward variable, but the forward variable. Therefore, it's well known that given any diffusion process, there are two associated PDEs, namely Kolmogorov's forward and backward equation. This is going to be kind of a mixed equation, so they just call it as a Kolmogorov equation. All right? And what this is going to, if you call this as some, what would this solve? This would solve the following problem. I'll just call it as, it's a function of t and x. I'll just, instead of putting all these s sub t, phi and so on and making it harder to read, I'll just call it as derivative of f with respect to t to be equal to the I'm just writing. It has to be the derivative df and dst phi and so on. To make things easier to understand, I'm just f prime b. B is the drift part plus f double prime over 2 sigma square. This is how we usually write, correct? So this is the whatever happens in the dt part, and sigma is the coefficient for the noise part. And that's called together, that's called the generator. You can, I'm just showing you as though it's all one dimensional, so that you get your mind's eye. And then this is actually an initial value problem. And Tx would be phi of x. So this is called the Cauchy problem corresponding to diffusion processes, right? Wherein it's neither backward nor forward. So it's just Kolmogorov equation. It ties in well when you operate with semigroups, that's why. And so here f was actually a function of t and x. So what is f of tx? It is this part. All right. Supposing you make it as follows. Replace.
That's an interform.
Well, but then in the Ito formula, the drift will be there and the expectation will be outside. And I had to take it term by term inside, right? So that's where a lot of the effort is expended. So I'll have expectation of all these things with the random processes inside. But to make it like this, wherein S of t phi is already having that. So I get to bring the f prime out, b, and then have the expectation just for this part and so on. So it amounts to taking expectation term by term somehow in an operator with non-constant coefficients. So define. So what is the f of tx? It is just another name for st phi of x. Define a function called, let's say, g of sx, let's say. So all right. Apply the Ito formula for this g. You all know the Ito formula, right? The students. Typically, you should know this. The Ito formula is the change of variables formula, and wherein there is an extra term that comes in, right? I can write it later if you want me to. And that's the fundamental thing that you learn, one of the things that you learn in stochastic analysis. Apply the Ito. So you think of this for g as a function of s and u of x comma t, u of x comma s. U of x comma s. Then what you would get is, since you are flipping the time, this derivative with respect to, when you do it with respect to s, there will be a minus sign that comes in. Then what will happen is derivative of g with respect to s, so it can be taken to the other side. That's all. So here the b for us is the capital F, right? The a and the capital F and all that. The action of all those. So this would become 0. Then the initial condition here would be only there as a terminal condition, right? You understand? I could even put a capital T here if I wanted to. So you just flip the problem. That's all there is to it by reversing time. And therefore, everything is on one side and it is all equal to 0. Correct? Now, what should you do the Ito formula? You don't have to do the Ito formula. This is all deterministic. Okay, now do Ito formula. Okay? Now do use Ito formula. Do G. Yeah.
In the last formula, is it f or g? F prime or g?
F prime. Oh, G. Everywhere G. Thank you. It's all G. Yeah. Very good. Sometimes I get to make those to see. Yeah, if you're following. It's a lame excuse, right? Okay. u c2 to g of t comma u of x comma t, then what happens? You should get on the right hand side, I should just get this phi of x. How did I get? Because here is phi. All right, that's correct. Then at time t I have phi of x, that should come on the right hand side, correct? Phi of u of tx, u of xt, phi of x. Because I changed time and so on. And here there is this st phi of x comes in. And then what happens? I have to think of this because there is nothing here. I don't have actually a proof here. Just give me one minute. St and phi. Oh, yeah, because I said that my f actually stands for st of phi. I forgot that. So what I will get is the following. I'll just write down. Phi of u of xt equals st phi of x plus integral 0 to t phi of sx sigma deta. Okay, let's look at it now. So there was a convolution integral, which is why there is an s sub t minus s. What happened to when you apply the Uto formula, there has to be a drift term. But the drift term is all 0 because of our choice of g. G is associated with f, right? Nothing but time reversed. Do you all remember these kind of equations? It comes often in applications, wherein you have to reverse the time. And therefore, this is what you get. We have made the drift to be 0. Therefore, there is only a stochastic integral here. Okay. And therefore, now multiply this equation by whatever you need, sigma inverse, Vz, and so on. Multiply both sides by integral 0 to t sigma inverse V sub z of Sx. Then what would happen? You multiply, this is a constant term, correct? There is nothing random here because you have taken the expectation. It is expectation of phi of the process at time t. So when you multiply by a martingale and then take expectation, it becomes 0, right? Multiply both sides by this and take expectation. You should all remember that I'm doing a lot more for a proof within inverted commas. Huh? Okay. Then on this side, I have phi u of xt or tx, whatever it is, times this integral 0 to t sigma inverse Vz of Sx dws. Do you all remember that this is what we had in the Bismuth-Elworthy formula? And this would be equal to, now this times this and then take expectation, I told you just now it is 0. And then these are two martingales because they are dw and dw, I call them as martingales. Whenever there is a stochastic integral, it should be a local martingale. then since it's dw and the bracket process for it is ds, it would become as integral 0 to t. You have to just multiply the integrand sigma, and then this comes in bz ds. I have expectation, but then when I take expectation, the sigma inverse cancel out. Now what is this? DST phi. DST phi. ST minus S phi. So what is this? DST minus S phi of Sx. That means I'm looking, I started at little x. I'm going to put in here what happened at time s. We never use this kind of a notation. That's why it bothers me. But then I introduced it already. I should have written it all as in terms of expectation. Okay, let me do it here. Give me. All these do not make sense. Yeah. All right. Sorry about that. Otherwise, it cannot have two values, right? So what I'm doing here is I'm going to take the expectation for t minus s more units of time, right? Phi, in which s units of time have already elapsed, and I'm looking at the state of the process at time s. Therefore, t minus s and s add up to t, correct? Because we have the semi-group property. Therefore, all of these can all be written as s of t phi of x, correct? And then of course I have the d's too. But then this has nothing to do with s, so I can pull it out of the expectation. Okay. And then I can make use of this also, so that the d corresponds to this u sub z comes in because of chain rule. So what do they all come out to be? It will exactly be, this part will exactly come out to be it's a little bit, so all of these can be written as this one, d is t phi of x v. So that's it. DST phi comma z. Yeah, there is a z here. That's just in the evaluation part. ST phi of x comma z. So that's all in the, that's a constant actually as far as the time integral is concerned. Therefore, I get to multiply it by t. So my claim is that the integrand reduces to dst phi of x. All right? And this is amazing actually when I saw it the first time, that you can actually take expectation of Borel measurable functions of a diffusion. That's not so easy. If it is a CB2 function, namely twice differentiable function, you can use the Ito formula. What do you do if it is just bounded Borel measurable? You cannot do, right? Whereas here you can actually pass to the limit and so on, and get hold of the expectation of Borel measurable functions of the random variable. First time I was very, very thrilled. The second time I thought, it kind of, after a week I thought, well, after all we are finding expectation of a bounded Borel measurable function of a diffusion, but then there is a semi-group, therefore it's really a convolution integral. So you can always transfer derivatives and all that to the convolution integral, right? Therefore, though we started with something rugged, it's going to be smooth. So, but then it's easier said than done. So this is a nice trick. Okay.
It's very important to have sigma in R. I mean,
You are right.
Otherwise, it falls.
Exactly. Sigma inverse.
So it is the cancellation term that plays the role.
That's right. That's right. You are right. So that's why we assume that sigma is invertible. Did I write those?
Yes, sigma inverse is there.
Right. Right. Sigma is invertible, and it was sigma inverse is a bounded operator. Right. It's a continuous operator. Right. That we need. Yeah.
That is basically smoothing the.
That's right. That's right. Okay. So before we, I'll just take a couple of minutes and then finish the Strongfellow property. So Strongfellow. So this is actually a theorem. Okay. With all the above hypotheses. ST is strong. Proof. Very simple proof. I'm not going to spend much time at all. We are done almost. So, let F be CB2. Note that we only started with a Lifschitz function capital F, but it can always be approximated by CB2 functions on H. Therefore, I'm going to just do it for this. And what we can do is, for any z, let's consider the following. ST P of x, comma z. By this formula, the t comes downstairs here, okay? So I'm exactly considering what I have here, and I have squared it as well. Therefore, there is a 1 over t squared, and I had to write all these things. So let me just sigma inverse Vz of Sx dw. That's what I have, right? And that can be bounded by 1 over t squared. The phi, I'll just put the sup norm for it. And the sigma inverse is a bounded operator. Okay. And what else is to be estimated? Then there is this part. We all know from the E2 isometry how to write it, correct? And but then the sigma inverse has, that's why been taken out. I'm using the E2 isometry. And then that's how it will come out to be. Very simple, right? Oh, but how did I take the square inside? I think that's all right. Yeah. And do you all recall that the Vz, we got it to be less than or equal to a constant times absolute z? That was part of our theorem on differentiability, right? So this will all become c squared z squared. This part can be then written as t times c z squared by using this. Okay? So what happens is I have a hold on this dzt of phi, and z is arbitrary. Therefore, I can remove the squares from everywhere. That's not a big deal. Therefore, what is st phi? I can use this bound after taking away, but I take a square root on everywhere, right? The t and t squared cancel to give me a t.